Hello, in this lesson we will answer one precise question. After obtaining y prime equals minus f sub x divided by f sub y, why must the second derivative again use a total derivative along the curve? We will begin before imposing f equals 0 and proceed one mathematical line at a time. First, forget for a moment that f of x comma y may later be equal to 0. Suppose simply that u equals f of x comma y. The output u depends on two inputs x and y. Think of the xy plane as the input floor. Over each input point the value u is represented as vertical height. A movement in the input plane can therefore cause a vertical change in the output. Now we are given one additional relationship. The variable y itself depends on x, therefore once x changes, y does not remain independently fixed. After substituting y of x, u becomes a composite function of the single variable x, differentiating u with respect to x. Begin at the point P whose coordinates are x and y of x. I deliberately choose only a small change delta x. I do not independently choose a second arbitrary change for y. Because y equals y of x, the chosen change in x automatically produces the corresponding change in y. Delta y is y of x plus delta x minus y of x. It is determined by the path. Although I initiated only delta x, both coordinates of the point change. This paired movement is the important idea. This is the total change in the output because the input point has moved in both coordinates. Divide the total output change by the chosen change delta x. This is the average rate of change of f while y follows x. Let delta x tend to 0. Because y of x is continuous, delta y also tends to 0. This limit measures how f changes as x changes and y follows x. As the second path point approaches the first in x, continuity of y of x makes its y coordinate approach as well. Therefore both coordinates approach the original point. To separate the two coordinate effects, add and subtract the intermediate value f of x plus delta x comma y. The first bracket measures the y change while x is temporarily fixed at x plus delta x. The second bracket measures the x change while y is temporarily fixed. Adding the brackets gives the original total change exactly. Divide by delta x. For the y part, multiply and divide by delta y. The result is a y partial quotient times delta y over delta x plus an x partial quotient. If delta y happens to be 0 for an increment, that y change contribution is already 0. In this quotient y is fixed and only x changes. Its limit is the partial derivative f sub x. In this quotient x is fixed at the nearby value while y changes. As both increments vanish, the quotient approaches the partial derivative f sub y at the original point. Because delta y was defined from y of x, the remaining ratio tends to the ordinary derivative dy by dx. Combining the limits gives du by dx equals f sub x plus f sub y times dy by dx. This is the total derivative along the path y equals y of x. Notice carefully, f sub x and f sub y are partial derivatives, but the entire expression is the total derivative with respect to x because the actual path changes both coordinates. Only now do we impose the implicit curve condition f of x comma y equals 0. We are no longer considering arbitrary points in the plane. We restrict ourselves to points whose coordinates satisfy f of x comma y equals 0. Near a regular point where f sub y is not 0, the curve may be viewed locally as y equals y of x. This is the local setting for the formulas that follow. At the first point on the implicit curve, the function value is 0. Now change x by delta x. The curve determines the corresponding delta y needed to remain on f equals 0. The nearby point also has function value 0 because that point is still on the same implicit curve. Along the curve f of x comma y of x is the constant 0, therefore its total derivative with respect to x is 0. The total derivative is f sub x plus f sub y times dy by dx. On the zero-level curve, these two coordinate effects cancel. Assuming f sub y is not 0, divide through by f sub y. The implicit slope is minus f sub x divided by f sub y. This formula is not describing an arbitrary change in y. It gives the slope of the implicit curve f of x comma y equals 0. From this moment onward, whenever we use this dy by dx, we have already accepted the condition f of x comma y equals 0. The slope is evaluated at a point on that curve. Now ask the real question, what does the second derivative mean? It is the derivative of the slope dy by dx. We are asking how the slope changes as the point moves along the same implicit curve. This sentence is the conceptual center of the lesson. The second derivative is the rate of change of the curve's slope while the point moves along that curve. Mark the first point P with coordinates x comma y on the implicit curve. Choose the nearby point Q with both coordinates changed. Delta y is the amount required by the curve after x changes by delta x. Both slopes must be slopes of the same curve, therefore both P and Q must satisfy f equals 0. Suppose we change x while artificially keeping y fixed, the new point will generally leave the implicit curve. This operation measures how an expression changes in the horizontal x direction with y frozen. That is a partial derivative. It is not the present question of how the curve's slope changes. For the correct comparison, changing x induces the corresponding delta y required to remain on f equals 0. Therefore, we need the total derivative along the curve. Freezing y would answer a different question. Let m of x denote the slope of the implicit curve at the point with first coordinate x. At the first curve point, the slope is minus f sub x evaluated at x comma y, divided by f sub y evaluated at x comma y. At the nearby curve point, both coordinates appear changed. This is essential because the second point must remain on the implicit curve. The second derivative is the limit of the change in slope divided by the change in x. This formula makes the geometry completely visible. We are comparing slopes at two nearby points on the same curve, so both x and y change between the two evaluations. Whenever a differentiable quantity depends on x and on y of x, differentiation with respect to x must include both effects. The derivative along the curve is partial with respect to x plus dy by dx times partial with respect to y. The first part measures the direct effect of changing x while temporarily holding y fixed. The second part accounts for the additional effect caused because y changes when x changes. The partial y effect is multiplied by the rate dy by dx. For any differentiable field g of x comma y, its derivative along the curve is g sub x plus g sub y times dy by dx. Recall that the slope is minus f sub x divided by f sub y, with both partial derivatives evaluated at the current curve point. This d by dx must not mean a partial derivative with y frozen. It means the total derivative along the implicit curve. F sub x is itself a function of x and y. Therefore, its derivative along the curve contains the direct term fxx and the induced term fxy times dy by dx. Similarly, f sub y changes directly through x and indirectly through y. Its total derivative is fyx plus fyy times dy by dx. If we now use the quotient rule, the derivatives of f sub x and f sub y are the total derivatives just displayed. the quotient rule does not permit us to freeze y. Assume f has continuous second partial derivatives nearby, then the mixed partial derivatives fxy and fyx are equal. For the cleanest calculation, return to the balance equation f sub x plus f sub y times y prime equals 0. Differentiate the entire equation with respect to x along the curve. The first term uses a total derivative, the second term also requires the product rule. The total derivative of f sub x is fxx plus fxy times y prime. Use the product rule, differentiate f sub y along the curve, multiply by y prime and then add f sub y times y double prime. Substitute the two differentiated expressions and expand. The two middle terms come from two different sources, but both arise because the point moves in y as x changes. Because fxy equals fyx, the two mixed terms combine into 2 fxy times y prime. Move the first three terms to the other side and divide by f sub y. This gives y double prime in terms of y prime and the second partial derivatives. Now substitute the already proved first derivative, y prime equals minus f sub x divided by f sub y. After using a common denominator and simplifying, d squared y by dx squared equals minus the whole numerator f sub y squared fxx, minus 2 f sub x f sub y fxy, plus f sub x squared fyy, divided by f sub y cubed. F of x comma y equals 0 means stay on the implicit curve. When x changes by delta x, y must change by the corresponding delta y required by the curve. dy by dx means the slope of that implicit curve at the current point. d squared y by dx squared means the rate at which that slope changes as the point moves along the same curve. Therefore, when finding the second derivative, we do not freeze y. We change x, allow y to change by the amount required by f equals 0, and compare the slopes at two nearby points on that same curve. That is why the differentiation is a total derivative along the curve. Keep this final chain in mind. F equals 0 means stay on the curve, changing x forces y to change. Therefore d by dx is the derivative along the curve both for the first derivative and again for the second derivative.